All right, let's talk about some type of new motion. We're going to expand our discussion to a new type of motion, that of rotational motion. Think of a bike tire that's spinning about an axle. The tire is really not moving across the room, but it is, so it's in some sense stationary. But it really is moving. It is spinning, and so therefore we need some new physics to describe what's happening here. We can talk about this type of motion in contrast to the type of motion we studied last semester. Something moving across the room is called translational motion, or simply just translation. That describes an object that changes its location in space, has time changes. We usually think of objects with little or no shape, like little point sources, that are moving across the room. This new type of motion is called rotational motion, or just rotation for short. This will describe the motion of an object as it rotates about some fixed axis. This typically has a physical size and shape, like a tire, a door, or something that rotates. Most of the world consists of things that both rotate and translate. Fortunately, we have physics that can describe rotational motion. But that's mostly a topic for another day, like AP Physics. Here, we're going to limit our discussion to forces that cause an object to rotate, and that's enough. In translational motion, forces are what causes objects to change their state of motion. In other words, a force is what causes an object to accelerate. If I apply a force to a point-like object, I will cause that object to speed up or slow down and or possibly change direction, like move in a circle. We talked all about this in last semester, so you should be fairly familiar with this. We have an analogous concept for rotational motion. A force that causes a physical object with shape and size to rotate about some axis is called a torque. It's pronounced torque. It rhymes with fork. If I apply a torque to a physical object, I will cause that object to either rotate in a clockwise or counterclockwise sense about the axis we're talking about. So a torque is going to be a force that's applied to a specific location on my object that will cause my object to rotate about some fixed axis. Mathematically, here's the equation. Torque is equal to Fr times the sine of theta. This equation, while it looks really simple, can be a little bit complicated. The symbol for torque is the Greek letter tau. Force, or F, is the force that is applied. The combination of r sine theta is called the lever arm. It is the perpendicular distance between the line of force that's applied, we call that the line of action, and then the axis of rotation. The angle theta is defined as the angle between F and R. But there's going to be an easier way to define this. I'll show that in the next couple of slides. The units of torque are Newton meters, Nm. Not nanometers, don't confuse it with that. It's really two units smashed together, Newton meters. Make sure that the force is given in newtons, that should be pretty simple, and that the R is given in meters. That's usually what slips people up. We usually have distances that are maybe in centimeters, so you have to make sure you convert them to meters. Make sure you do that. Torque depends upon two different things. One, it depends upon the amount of force that's applied. And two, it depends on where the force is applied. Hopefully the next couple of slides will make this clear. Here's an example of a force that's applied to a tire. Notice and be aware of what the line of action and the lever arm are. We have a tire with the force applied at the edge of a tire. Here's my tire. The X represents the axis of rotation. I'm applying a force at the very edge of the tire. Notice if I push right there, I'm going to make this tire rotate. I believe in this case it's going to rotate in a clockwise direction. Again, the X is the center or the axis of rotation. Think of an axis that would extend out of the paper. This dotted line is going to be the line of action. Notice I just extended the direction of the force in both ways. I have a little black line joining the axis of rotation and the distance between or to the dotted line. That's what we're going to call the lever arm. In this particular case, the angle that acts between the force and this R happens to be 90 degrees. That means my torque is going to be Fr sine of 90. Sine of 90 just happens to be 1, so it's just going to be Fr. This will be the usual case. Most of the time, and to keep things simple for honors physics, we're going to deal with forces that are perpendicular to the axis of rotation. That way the torques are not going to have any angles to deal with. Here's another example of a force applied to a tire. Again, be aware of where the line of action and the lever arm happen to be. However, in this case, the force is not acting at the edge of the tire. So here's my tire. I still have the dotted line in there. I'll show you what that means in a second. Here's my force. Notice that the force is not applied at the edge of the tire anymore. It's still going to cause this to rotate, but not quite as much as the previous example. There's my line of action. So that perpendicular or that dotted line that goes horizontally across the paper will be my line of action. The other perpendicular, the other dotted line between X and the line of action is going to be my lever arm. Notice it's not quite what the radius is anymore. It's a little bit less. There's my radius. Notice that my R and that my F are no longer perpendicular to each other. I need to find that perpendicular distance. I need to find that small dotted line. Well, here's an angle theta. So now, using trigonometry, I take the opposite times the hypotenuse. That's going to be my lever arm, so that's going to be r sine theta. That's where that term comes into play. In this case, my torque is going to be a little bit less than just Fr because the sine of my angle is going to be less than 1. Here's another example of a force applied to a tire. Again, be aware of the line of action and what the lever arm is. However, in this case, the force is not acting along the edge of the tire, but directly towards the center of the tire. I have the tire. There's my tire with my axis of rotation. I have my force, but now this force is pointed directly towards the center. You should see, and this should be fairly clear to you, that if I push on the force directly towards the center of the tire, I'm not going to cause the tire to rotate. Another way to say this is by drawing in the line of action. Notice that the line of action goes directly through the center or the axis of rotation. That means my lever arm is actually going to be 0. There's no distance between where the line of action acts and where the axis of rotation happens to be. That means the radius is still the radius of the tire, but now the lever arm happens to be 0. If my lever arm is 0, it means that my r sine theta is 0. That means that my torque is going to be 0. In this particular case, I cannot make the tire rotate. What does this mean? As I said before, in this case, this particular force does not cause the tire to rotate. If I apply a force directly towards the center or the axis of rotation, I can't make things rotate. Here's a few examples. Number 1, consider a force of 15.0 newtons that acts at the edge of a tire of radius 25 centimeters. What's the torque exerted on the tire? This is easy, although you have to remember to convert the 25 centimeters to meters. Always make sure you're using the right units. Here's the equation. Torque equals Fr sine theta, 15 newtons times 0.25 meters times the sine of 90. Sine of 90 is 1. When I multiply everything together, I get 3.75 newton meters. Not too bad. How much force do I need to exert to the edge of a tire of radius 33 centimeters to produce a torque of 10 newton meters? Well, this just rearranges the equation around. Use the same equation, but now solve for force. So I would have 10 newton meters divided by 0.33 meters. That's the R. My angle is still 90 degrees, so the sine of 90 is still 1. When I do this math, I come out with a force of 30.0 newtons. What is the torque exerted on a 2.5 meter tire? That would be the radius. If the force of 50 newtons acts at an angle of 30 degrees with respect to the axis of rotation. Plug and chug again. Fr sine theta, 50.0 newtons times 2.50 meters. But now my angle isn't 90. I gave you the angle to be 30 degrees, so I put in the sine of 30. Doing all that multiplication together, I get 62.5 newton meters. Hopefully that's not too bad. This is a brief little example on how to deal with torques and how to calculate torques. We're going to apply torques to something called equilibrium shortly. Enjoy.